We have just completed the section on properties of database transactions and database transaction statements. In this part, we will learn about the purpose of concurrency control, interference problems arising from simultaneous access to database, and tools of prevention and recovery. First, let's take a look at the purpose of concurrency control. What is concurrency control? Concurrency control is the coordination of the simultaneous execution of transactions in a multiprocessing database. The purpose of concurrency control is to prevent two different users or two different connections by the same user from trying to update the same data at the same time. Let's move to the next slide to learn more. Next, let's look at interference problems. Examples of interference problems which can arise from simultaneous access to a database are lost updates, uncommitted dependency, and inconsistent retrieval. Click on each button to learn more. Lost updates. Lost updates occur when two or more transactions select the same row and then update the row based on the value originally selected. One user's update overrides another user's update. The last update overrides updates made by the other transactions, which results in lost data. In this example, the stored value is 35, which then has 100 added to it and is now 135. When the second transaction takes place, this value is decreased by 30 and becomes 105, which overwrites the first transaction value of 135. Uncommitted dependency. Dirty read. This occurs when one transaction reads data written by another transaction before the other transaction commits. The stored value for the first transaction is 35 plus 100, 135. But then the second transaction has already accessed the uncommitted data. So now the value is 135 minus 30, 105. Next, the first transaction is rolled back, so the automatically stored value for the first still remains 35, but for the second will be 105. Inconsistent retrieval. This occurs when a transaction reads several values, but another transaction updates some of the values while the first transaction is still executing. First, the value is 8 and total remains 8 for the first transaction. Second, the value is 32, so the total will be 32 plus 8 resulting in 40. Third, the stored value for second transaction is 15. Fourth, the value of 15 is increased by 10 and now becomes 25. Fifth, the value remains 25 for the second transaction. Sixth, getting back to the first transaction, now the value 25 will be added to 40 giving 65. Seventh, add the value 23 and the total will be 65 plus 23 and 88. Eighth, getting back to second transaction. Now the value still remains as 23. Ninth, the value of 23 is subtracted by 10. 10th, now this value becomes 13. 11th, the second transaction has rolled back. 12th, going back to the first transaction, 8 is added to 88 giving 96. 13th, we add 6 to the value of 96 giving a value of 102 for the first transaction. The situation illustrates inconsistent retrieval which occurs during simultaneous access to a database. We have learned about interference problems arising from simultaneous access to a database. Now, let's examine the tools for preventing these problems. Locks and two-phase locking protocols known as 2PL. Click on each button to learn more. Locks. A lock is a procedure used to control the concurrent access to data. When one transaction is accessing the database, a lock may deny access to other transactions. There are two major types of locks: shared lock or read and exclusive. As the names suggest, a shared lock can only read information, but an exclusive lock allows information to be updated. The two-phase locking protocol, 2PL. This protocol utilizes locks that block other transactions from accessing the same data during a transaction's life. 2PL protocol locks are applied and removed in two phases: expanding or growing and shrinking phases. Phase 1, expanding or growing phase, is when locks are acquired and no locks are released. The growing phase, in which a transaction acquires all the required locks without unlocking any data, is shown in this figure. Next, phase 2, shrinking phase, is when locks are released and no locks are acquired. The shrinking phase, in which a transaction releases all locks and cannot obtain any new locks, is shown in this figure. Next, recovery tools are used to restore a database from a given state, usually inconsistent, to a previously consistent state. There are three recovery tools for database transactions. These are transaction locks, database backups, and checkpoints. Click on each button to learn more. Transaction logs. A transaction log records all transactions and the database modifications made by each transaction. It's a critical component of the database, and if there is system failure, the transaction log might be required to bring a database back to a consistent state. The figure shows the transaction recovery example for transaction log, which display all operations occurs in the database transaction and other important details such as the updated rows, updated attributes, before and after values for each transaction log. Database backups. It is important to be able to back up and restore databases. This provides an important safeguard for protecting critical data stored in a database. A copy of data that can be used to restore and recover the data is called a backup. Backups can restore data after a failure. With good backups as shown in this figure, recovery is possible following many types of failure including media failure, user errors, for example, dropping a table by mistake, hardware failures, for example, a damaged disk drive or permanent loss of a server, and natural disasters such as tsunamis, tornadoes, and meteor strikes. Checkpoints. Dirty pages are data pages that have been entered into the buffer cache and modified but not yet written to disk. Checkpoints save time during later recovery by creating a point at which all dirty pages are guaranteed to have been written to disk. If you set a shorter recovery interval than the default, the checkpoint process writes changes to the database more frequently, so it has fewer changes to write each time. If, however, you specify a longer interval, the SQL server lets more changed pages build up in memory before writing them to disk. Most end users don't notice checkpoints, although a long recovery interval could produce fewer checkpoints with a more noticeable slowdown of operation.